Hello, my name is James Roberts. I am a senior at the University of Connecticut studying biomedical engineering. My faculty mentor for the McNair Scholar Program is Dr. Ramesh Malla from the Department of Civil and Environmental Engineering. The title of my project is Stress and Deformation on a Pressurized Dome Lunar Structure Under Various Depths of Regolith Cover. The Resilient Extraterrestrial Habitat Institute, or RETHI, is a NASA research project. Their goal is to develop the technology to establish habitats on the moon. The goal of my research is to understand the effects of a pressurized interior dome on the walls of the structure. The walls will be made out of concrete. Concrete has a low tensile strength, thus it will be important to understand the stresses inside the wall of the structure. Also, it has been seen that regolith or lunar soil could be used as a material to protect the habitat from radiation. My objectives are to use Abaqus, a finite element analysis software, to understand how different wall thicknesses affect the stress within the walls. Also, how different depths of regolith cover affect the stress within the walls. From literature review, I found the required elements to conduct my finite element analysis. I keep in mind that the tensile strength of concrete is 2,000 kilopascals. The dome has a thickness of 10 to 40 centimeters. Figure 1 is the dome part in the Abaqus software. Figure 2 is the mesh of the part. An internal pressure load of 101 pascals, or 1 atmosphere, was applied to the inside faces of the dome, and a Castray boundary condition was applied to the entire bottom of the dome. For the simulations with regolith cover, the dome dimensions was 10 centimeters thick. Figure 4 is the equation for solving for the pressure load on top of the dome. The cover had depths of 2 to 4 and 6 meters. Figures 4 through 7 are the results from the Abaqus simulation for a dome with no regolith cover from 10 to 40 centimeters thick, respectively. Figures 8 through 11 are the results from the Abaqus simulations for a 10 centimeter thick dome with regolith cover from no regolith cover to 6 meter regolith cover, respectively. Figure 12 is the graph for the max principal stress versus dome thickness, where the red line represents the max tensile strength of 2,000 kilopascals. Anything above the red line could result in failure. Figure 13 is the graph for the max principal stress versus regolith cover thickness, where the red line also represents the max tensile strength of concrete. Lunar concrete has a tensile strength of 2,000 kilopascals. Thus, all simulations where the max principal stress is above 2,000 kilopascals, the dome is likely to fail. The dome with the highest tensile stress is a 10 centimeter dome thickness with no regolith cover at 3,044 kilopascals. The minimum tensile stress for a dome without cover is 827 kilopascals at 40 centimeters dome thickness. This falls well below the tensile strength of concrete. The minimum tensile stress for a dome with a cover is the 10 centimeter dome thickness with a 6 meter depth of regolith at 667 kilopascals. This is the smallest tensile stress for all of the simulations. A combination of a slightly thicker dome and lunar regolith cover shows promise for in-situ resource utilization material. Future research should look at the abundance of water on the moon's surface. Large amounts of water will allow for larger dome structures. My future work is to continue on the project working on Abaqus simulations of lunar conditions and also working on our pressure box here at the University of Connecticut. I would like to thank and acknowledge Dr. Ramesh Malla, Dr. Sock, Jeffrey Steiner, Sachin Tripathi, Francesca Esperita, Neil Chakravarti, the Resilient Extraterrestrial Habitats Institute, the Department of Civil and Environmental Engineering, NASA, the McNair Scholar Program, and the University of Connecticut for this opportunity.